Hello, today I want to make a quick video how to create communication link between computer and microcontroller. I'm going to use FTDI microchip to convert USB to SPI. Now SPI is synchronous interface, but it's very fast. So as you can see right now, I am streaming live video from monochrome camera at 200 by 200 points and an 8-bit in 8-bit depth. So as you can see, this is a simple ARM Cortex M4 processor with a small amount of well, not small, 2 megabytes of SRAM, and the processor takes that data from sensor and sends to SRAM, and from that I'm doing conversion from 10-bit to 8 bits and storing my image inside internal memory. And the DMA controller takes that data and transfers to a computer. And as you can see, this communication link is running at around 12 frames per second. So it's not extremely fast, but it's one of the fastest way to get data without any problems or going to USB protocols and USB program that's quite difficult. So from LabVIEW application I can change many parameters, like I can change integration time, I can change gain, as you can see, system lag, picture in picture, I can change analog offset and so on. Okay, so first thing to do is to understand how to connect FTDI microchip. So we're going to read some data sheets and to try to understand. So this is I'm going to use. This is dual USB to serial chip FIFO and WAR, and I'm going to use SPI serial link. So what do we need to know? Okay, first thing to know, we are going to use a USB self-power configuration. So what we need is USB connector, we need resistors for protection, and of course for protecting for ESD we need to reset resistors, so this chip will be operational when we plug in, and we need to provide clean analog voltage, and also we need to make VCC for A and B channels correct one. That means we need to connect 3.3 volts, so like this. So this is configuration, basically what we are going to use. Now when we make this, so this is the base circuit. Of course we need to get there's two more things. We need clock, 6 megahertz, and we need also not flash but EEPROM. So this is clock generator circuit I'm using. It's very small crystal, and I like it because my PCB design is very very dense. And so this is provides a reference for FTDI microchip, and of course we can use this oscillator, and we need EEPROM so we can set device name. And this is useful because if we have many FTDI devices connected to a computer, we can distinguish which one is which one and which program we should load from LabVIEW. Okay, so now we need to understand where is SPI clock and master input slave output and master output slave input. Okay, and of course we need chip select, but because we are going to use DMA, we don't need chip select. We need chip select only to synchronize our circular DMA buffer. So these are the pins we are going to need. We're going to need channel 1, of course, because channel B don't have SPI. So we're going to use 24, 23, 22, and for synchronization 21 pin. Okay, now next thing to do is to download examples how to use this chip with LabVIEW. Uh, so we are going to download uh, this example. We need SPI example, and we simply download it. Of course, we need to install drivers and so on. And let's download it. So when we download it, we get lot of functions. So I will show how to assemble these functions to get program. Okay, so I made a program to send data and read data. So this is settings we need. So we need the clock pin high, we need data out low, chip select high, and we need this is MSB first. We need to get on the positive edge. We're going to send 8 bits per burst, and there is two ways, 8 or 16. And this is the buffer we are going to send, and this is how many times we are going to send. Not times, but array number. So if we're going to select 2, we're going to send 0. We're going to send 6, and we're going to send 124. Okay, and this is read. So we are going to read 16 bits. So we're going to read 2 charts. And okay, so one thing is I connected my oscilloscope to FTDI microchip, and we're getting this data now. New oscilloscopes around 1-2 years old always have decoding and triggering abilities. So if we're going to have very old scope, this is the view we're going to see. Now, of course, we can go and trigger on the chip select, so it will be a little bit more understanding. But still, this is not well. It is possible to understand what's going on, but this is not giving us very good idea what's going on with our bus. Now, Textronic was kind enough and sent me this oscilloscopes to use it in my demos. And I'm very pleased by this oscilloscope. I mean, this is everything what you need. I only have a power supply. I only have also I have a hot air gun, and of course, 2 things I need is a microscope and a soldering iron, and that's it. This is all I need, and I can do everything I want. And if you have setup like this, and you can produce circuit, and you say I'm limited by my equipment, well, this is not. If you have scope like this is not excuse. And if it is truly best instrument you can have on your bench to for digital and analog use. This is have a frequency generator. This is have a spectrum analyzer, very high bandwidth of inputs, 16 channels of digital inputs, and of course it has around 126 picosecond resolution in the digital domain, so digital analyzer. Okay, so what I'm like about the scope is we can recall our setup. We have setups, so we can recall setup, and already made correct setup for SPI triggering. Now this is SPI decoded and displayed in the so it can be understood by humans. Now if we look to our program, we are sending right now 2 bits. Well, first is 6, and the second control bit is 124. Okay, and so what we are going to get, So this is exactly what we're getting. We're getting 6, and well, this is in the hex, so we need to convert it. And I think it should be somewhere in the how to bus display. We can display in binary, and we can display in hex, and so on. So okay, so we established that this is how many control bits to write. This is number, and this is numbers we are going to write, and this is how many bits we are going to read. Now this will be very important when we are going to assemble our buffer in DMA controller, and we are going. So we need to know this. We need to know this data, where we are sending data with DMA into which part of array, and from which part array we are reading data. Okay, so I'm going to take a paper and explain everything you need to know about this. Okay, so right now we need to understand how to manage data inside a microcontroller and LabVIEW. Now, inside a microcontroller, we will we'll create some kind of array. So this is a receive buffer, and this is transmit buffer. And inside LabVIEW, we'll have transmit buffer and receive buffer. Okay. Now, there is one critical thing to understand. Microcontroller is capable of reading and writing data from SPI at the same time with DMA controller, and LabVIEW with FDI microchip can only write and read at once. I mean, one time. So if it's transmitting, it can receive, and it's receiving, it can transmit. So this is the core principle to understand. So if we are sending, like right now, we are sending like 6, 7, 8, 9. Okay. So I mean, this is we are transmitting 6, 7, 8, 9. So we are creating buffer of 4 times 8. Okay. So this is how many chars, and this is how many bits per transmission, and this is what we're going to receive. So this is index 0, this is index 3, this is index 0, this is index 3. Okay. Now, how about these guys? Now, it's transmitting only this portion, and it's not and LabVIEW don't do anything. So data, this data is not used. So we cannot use this data for anything now, because every time we do something, DMA controller will do weird stuff with this part. Now, when we go into transmit, so we are transmitting like 1, 2, 3, and 4. So this is our array index of 4, 5, 6, and 7. Okay. And so, but inside LabVIEW, this index 0, 1, 2, and 3. So at LabVIEW part, we are going to get data like this. Okay. So, and again with RX buffer, because we are transmitting only four characters, this part is not used by FTDI. But inside here we're going to get 0 or 255, because bus can be only high or low. So this part we must ignore. So this is the fundamental problem. We are if we have very long array, let's say for my live image streaming, I'm having 40,000 array receive and RX at 8 bits. So at receive, I'm only using like set integral, exposure, gain, analog offset, and so on. It's very short, and it's like and this is how only few words are used, and this is not used. So this is basically going to infinity, not infinity, but very long array that we cannot use. And with transmit, we have very small amount of unused array, and after that we have image data. Okay, so this is what we need to understand. We are sending and reading from LabVIEW at once, not in parallel, but microcontroller is capable of sending and reading at the same time. So only this data and this data is useful. Now, second thing to note is how we configure our DMA controller. Now, DMA controller, what DMA controller will do? It will send this to SPI. It doesn't, because it must send everything, but we are not reading it. And of course it will read everything from SPI bus. Okay, so SPI DMA controller will be configured in circular mode, and it will have to read how many packets we transmit, transmit, and how many packets we will receive. And if we set this number to correct one from so it will when we finish our read write cycle, the DMA controller will jump to the first one, and it can read and read and read and read, and we don't need MCU to do any work. I mean, this can be static, and microprocessor can do some calculation, can do some painting to the screen, or do some complex calculation. It doesn't need to manage all of this if it's in the circular mode. If it's normal mode, after chars are sent to the SPI, it will generate transfer complete interrupt, and we need to reset our buffer. We need to reset our address. We need to reset our how many counts, how many buffer length, and we need to clear all the flags from special DMA registers. So again, we are transmitting only once, one time. It will go to this part. We are receiving from this part, and DMA it's number. DMA is how many we are transmitting and how many we are receiving. And so that's it. That's it. This is what we need to understand. Now I'm going to show how to create a program inside LabVIEW and inside microprocessor, so we can exchange data. Okay, so now I'm going to explain how to connect SPI to GPIOs and how to configure a DMA controller. Okay. Okay, first thing to do, we need to select. I'm using STM32 CubeMX for pin configuration. Okay, so let's say we're going to use SPI1. Okay, and we're going to use as a full duplex master, and we're going to use GPIO A3 as our external input. So this will generate. This will, okay, let's go to the bottom. This will generate interrupts. This will be clock input. This will be master input, slave output, and master output, slave input. Okay, so we already established we only need 4 pins. Of course, ground we need, but that's normal. Okay, let's go to the program. So this is SPI configuration. Okay, first thing to do, we need to select correct clock. Okay, SPI1 uses APB2 for clock source. Now SPI like 2 or 3 will use different APB1. Okay, so we need to set correct bus for our peripherals. Well, no, not bus, but you get the idea. So we need to use SPI1. And of course, because we need to use correct enable function for the clock, so this will enable high-speed peripheral clock. Okay, APB2. So this is good for SPI1, and APB1 is good for SPI2 and 3. So this is very important. If we select SPI2, we will get errors. We will not going to get any data. Okay, now we need to enable DMA clock. Now, which DMA should we use? Now, it's very simple. we're going to go to reference manual. Okay. So this is program. Yes, this is reference manual. Okay, you can download this datasheet, not datasheet, manual from ST. It will explain everything you need to know about microcontroller and how to use it. So let's go back to the DMA channel selection. This is what we need. Okay, there are two DMA controllers, DMA1 and DMA2. Now, if we're going to look at DMA1, let's focus. There is no SPI1. There is SPI3 and SPI2 and other peripherals and SPI3. Okay, so DMA1 is not good for us. We're going to use second DMA. Okay, let's refocus. Okay, so channel 3 is perfect for us. We have RX stream and transmit stream. So let's see if our configuration is correct. So this connects. So we are going to use DMA2. Now this will connect GPIOs to this part connect GPIOs to the alternate function. Okay. So because each pin can be as a normal general purpose I/O and also can be an alternate function that will be SPI. So we select 5, 6, and 7 pins as SPI1. This is input configuration. This is we need to select as full duplex. Size must be 8 bits and the prescaler must be master should run faster. Master should run slower than slave, and slave must run faster. And because master controlling slave and slave is faster, we're not going to get errors. So basically, our SPI peripheral can keep up with SPI clock that it's getting from master. Okay. So now this is where it gets interesting. So we already established that we need stream 0 for receiving bits. Okay, stream 0. Okay, stream 0 from receiving and stream 3 for transmitting. Okay, first we disable just to be, well, that's good practice. Okay, that's buffer size. Buffer size is how many we are getting from LabVIEW and how many we are requesting data from LabVIEW. So I made simple program. So RX plus TX. So let's see, 4 and 4, 4 and 5, doesn't matter. It can be anything between 0 and 65535. Okay, that's a lot of data. What else? Okay, now of course we select an SPI1, so our peripheral address, and now this configuration of DMA streams. Now we are selecting channel 3. Okay, look, channel 3, and we are using for receive we are using DMA stream 0, and for transmitting we are using DMA stream 3. Okay, and we are enabling streams, and we are enabling request. Now if we run through this code, it will start transmitting data if master is generating SPI clock. Okay, it's all it cares about, SPI clock, DMA controller. And of course we are using a third pin of GPIO-A as our interrupt for DMA configuration, and this is interrupt program. So each time this transition happens, so it's high, this high, low, high, so we are falling edge. So here at this point we will configure DMA controller. So at this when we done it, when we execute this part of code, we know what DMA controller is set at the first pointing at the first array index. Okay, and that's it. So we are so what we need to enable? We need to enable external interrupts. Okay, so that's all we need to enable. And external interrupt vector program will enable SPI, and communication will just happen magically. Okay, so let's get to another part of this tutorial. Okay, so I connected 3 SPI lines, clock, master input, slave output, and master output, slave input, and of course green is CS and is working as the interrupt. Okay, Now let's go to the program. Let's focus a bit. So what I need to call external that will configure our interrupt. So free third pin of A is connected to the channel 3 XT, and it will initialize our SPI. So we already know that. So what I did is made simple code. This is while loop. So I'm simply reading A, B, C, D, and I'm writing to delay. Now because it's volatile, I should create sum this one by one, so there is no violation in volatile operands. So this is why we have this triangle. But of course it will going to work. And I'm sending 1, 2, 3, and 4. Let's say 128, 1 to 8. Okay, so and in LabVIEW we have array A, B, C, and D. So it will correspond to our variables, and we have Eric's how many packets we're going to receive, and this is Eric's buffer, and we have some status. Okay, so first thing to do is to program microcontroller, and we are having so we are watching live A, B, C, and D. Because it's not connected, it is 0. Okay, so let's connect it. And straight away, if you look closer, you will see that we are getting data. So, and of course, let's see. So this is 1 to 8. This is 3, 2, and 1. So this is corresponding to numbers in here. Okay, and if we change numbers in here, we will say that A is changing, and B is changing, and C is changing, and D is changing. So we know that everything is working correctly. Now, one thing to note, it's more than 1 kilohertz update rate. So I'm getting updating variables 1 kilohertz. And you see how difficult it is to write programs. So this is everything what we need to for reading data and for sending data. It cannot be simpler. And of course, there is only one problem. If you have large variable like 32 bits, we need to assemble it from 4 numbers, and it is possible to write to this number and read it, and we will get corruption. So basically, we have 2 bits, 2 bytes from one transmission and 2 bytes from second transmission. If data is very rapidly changing, we will get errors. But we can make this we can fix it with simple CRC. But for now, it will work. So let's make something useful. So I'm going to write program for transmitting temperature of die to LabVIEW and showing into the graph. So I will be back in a few minutes. Okay, so I made simple program how to read temperature. Okay, first thing to do is initialize ADC. So, well, this is simple program how to do that. So we select that mode is independent, that we have prescaler 8, we have 5 cycle delay, resolution is 12 bits, so we have over 4000 data points between our 0 and reference level. It's data right aligned, so it's normal and not inverted, and then we need to select correct channel for temperature, so it's channel 16, and we enable temperature sensor and enable ADC now, and start AD conversion. Now this is how I read ADC. So I have 16-bit variable, and I wait for ADC to complete conversion, and I read data and transfer it to mine. Now in mine I have 16-bit variable. Now 16-bit I need to split into 2 because I only have 8 bits 8 bits variables in my transmit and receive array. So I simply 0 will represent most significant bit and one least significant bit, and I have to assemble this in LabVIEW. So I need to do this inside LabVIEW. And how do I do it? So this is how I do it. Now I'm taking array from SPI read, and I'm taking 0 channel and making as upper bit, and I mean not channel, zero index of array is most significant bit, and first is a lower bit, so it's least significant bit. So I am so let's make it visible. Okay, so my reference level is below 3 volts, so I multiplying and divide it, so I'm getting volts. So I'm dividing to getting millivolts. Millivolts, I'm subtracting my reference voltage at 25 degrees, and I'm dividing by slope. That's 2.5 millivolt per Celsius, and adding a reference voltage at 25 degrees, and I'm getting my temperature. Okay, so this is simple graph what I made. Okay, so first thing to do is program microcontroller. Okay, it's program. Okay, so let's just quit, and we will start LabVIEW. Okay, application, and we should start to see a temperature. Okay, as you can see, we have around 30 degrees of temperature, because this is temperature of the die, or not ambient temperature. So, and because processor is running at quite high speed, so it's a bit ambient. So what I'm going to do is I take my hot air gun. Okay, I set to 100 degrees, and I'm going to heat my processor. Well, I'm not going to kill it, but temperature will rise, so we can see it on the graph. Okay, so I'm starting to heat, and as you can see, temperature is going up, and of course it will slow down because we have a lot of thermal mass. And I remove the heat, and we can see that temperature is going down. So it's very simple application. And one thing to note, if you look at this is how many sample numbers we get from microprocessor. So in each second I'm getting more than 1,000 samples. So, and I'm getting no errors. So this is very nice way to communicate with the computer. Now if we look at mine, processor, as I said before, processor don't even know that I'm communicating with a computer, because I'm storing my data inside array that is in memory, and DMA controller takes that data in circle fashion and transmit to LabVIEW. And as long as buffer size is correct inside LabVIEW and inside inside LabVIEW and inside DMA configuration, I will not going to get errors. Now look what happens if I change, like I'm getting not 4, so I'm receiving 4 bytes, okay? 4 chars. Let's make it 5. So my circular buffer will here. My circular buffer will be out of sync. Well, let's see, because I'm syncing only once, and right now I will get errors and errors, okay? As you can see, I'm getting nothing. So data is corrupted. And if I go back to 4, that is correct. Okay, so now it's 5, okay? And I'm getting errors, many errors. So I'm changing receive to 5, okay? I mean transmit buffer, it's 5, not 4 anymore, okay? So I'm reconfigure it. Okay, let's give it a second. Let's reconfigure it. So I made it 5. And now it should start to work again. Let's see, am I correct? Yes, of course it works. So this is basically it. Okay, so thank you for watching this tutorial. If you like it, please press thumbs up. If you don't like it, press thumbs down. Any feedback is welcome, and I will create many more videos about STM32 because this is my favorite platform. And of course I want to say thank you again for Tektronix for sending this oscilloscope. It really helps to develop application like this, like these. And so, okay, see you next time. Bye.